Hello students, myself is Jyoti Kiran, Assistant Professor, Government First Grade College, Tiptur. Today I am going to discuss on the concept curvature and radius of curvature for the curves given in Cartesian form. First we see the definition of a curvature. So from the figure we can explain by taking the figure. Let P be any point on the given curve. So here this is the curve. Let P be any point on this curve and Q be a neighboring point. Here Q is there. It is a neighboring point to the P. Let arc AP. This is the arc AP. Its length is small s and arc PQ. This is the increment. From the point P, this is represented by del S. Let the tangent at P and Q make the angles psi and psi plus del psi. So this is an angle made by, along the x-axis made by this tangent psi, and this tangent made by the angle psi plus del psi with the x-axis, so that the angle between the tangents at P and Q is del psi. So this is the angle between these two tangent del psi. Therefore, the average curvature of the arc PQ. The average curvature of the arc PQ is del psi by del S. The limiting value of average curvature when Q approaches P is defined as the curvature of the curve at the point P. Then the curvature K at the point P is defined as d psi by ds. So this will becomes, after applying the limit del psi by del s, it will becomes d psi by ds. Okay, next we move on to the definition of radius of curvature. The reciprocal of the curvature of a curve at any point P is called the radius of curvature at P, and it is denoted by, radius of curvature is denoted by rho is equal to 1 by k, which is equal to 1 by k is d psi by ds. In the previous slide we discussed on k is equal to d psi by ds, which is equal to ds by d psi. Next we move on to the definition of center of curvature. A point C on the normal at any point P of a curve at a distance rho from it is called the center of curvature at the point P. Next we move on to the circle of curvature. A circle with center C, center of curvature at the point P, and radius of curvature rho is called the circle of curvature at P. Next we move on to radius of curvature for the curves given in Cartesian form. Let us see the derivation of a radius of curvature in Cartesian form. Let y is equal to f of x be the given curve in Cartesian form. Let psi be an angle made by the tangent at the point x comma y with the x-axis. In the previous slide we see that the angle psi is made by the tangent with the x-axis. We know that slope of a tangent dy by dx is equal to tan psi. Differentiating both sides with respect to x, we get d square y by dx square is equal to, differentiation of tan psi is secant square psi d psi by dx. Again, d square y by dx square is equal to secant square psi into d psi by ds into ds by dx with respect to the arc length, which is equal to secant square psi is 1 plus tan square psi d psi by ds, but ds by d psi is rho. Here d psi by ds is there, that is 1 by rho into ds by dx. Okay, then d square y by dx square is equal to 1 plus tan square. What is tan? Dy by dx o square into 1 by rho into ds by dx. Already we know this formula. ds by dx is equal to square root of 1 plus dy by dx o square. Substitute here. And simplifying this, here its power is 1 is there, it is 1 by 2, we get 3 by 2 into 1 by rho. But we have to find out the radius. Here rho represents the radius of curvature. Therefore rho is equal to 1 plus dy by dx whole square to the power of 3 by 2. On cross multiplication we get d square y by dx square. Therefore rho is equal to 1 plus dy by dx is the first order derivative, that is y1 square to the power of 3 by 2 by second order derivative is y2. Okay, thus the radius of curvature at any point x comma y on the curve is given by the formula rho is equal to 1 plus y1 square to the power of 3 by 2 is whole divided by y2. This formula is called the Cartesian formula for radius of curvature in terms of x and y. Okay, next we move on to the radius of curvature for the curves given in polar form, that is the curve in terms of r and theta. Okay, let us consider a curve r is equal to f of theta with the equation of the curve in polar form. Let psi be an angle made by the tangent at the point p of r comma theta. This is a tangent with made by the angle psi with respect along the x coordinates at the point P of r comma theta with the initial line OX. From the figure, we can observe the figure. We have the result psi is equal to theta plus pi. Psi is an exterior angle is equal to sum of the interior angle theta plus psi. Next, differentiate with respect to the arc length S. D psi by ds is equal to d theta by ds plus d psi by ds. Then d psi by ds is equal to d theta by ds plus d psi with respect to the angle theta d theta into d theta by ds. Again d psi by ds is 1 by rho, which is equal to, take d theta by ds is common, d theta by ds common, 1 plus d psi by d theta. Therefore, we know that tan psi is r into d theta by dr. Then take the reciprocal r divided by dr by d theta. Then tan psi is equal to r. Dr by d theta is the first order derivative r1, where r1 is dr by d theta. Again differentiate these with respect to theta. We get tan psi is secant square psi into d psi by d theta, which is equal to r by r1. Apply the quotient rule, differentiate, we get this result r1 square minus r2 by r1 square, 1 plus tan square secant square psi, again write down 1 plus tan square psi. Then d psi by d theta is equal to, on simplifying we get, this is from the quotient rule, then 1 divided by 1 plus tan square psi. Again d psi by d theta is equal to r1 square minus r2 by r1 square into 1 divided by 1 plus tan square psi is r square by r1 square. In the previous slide we see that tan psi is r by r1. On simplifying this we get r1 square minus r2 by r1 square plus r square. Again we have the result ds by d theta is square root of r square plus dr by d theta whole square. This can be represented as r square plus r1 square to the power of 1 by 2. Substituting for d psi by d theta and ds by d theta in equation 1, we get the required result. Thus, the radius of curvature at any point p of r comma theta on the curve r is equal to f of theta is given by rho is equal to r square plus r1 square to the power of 3 by 2 is divided by 2 r1 square plus r square minus r minus r square minus r2. Okay, next we move on to the example 1. Find the radius of curvature of the curve root x plus root y is equal to root a at the point a by 4 comma a by 4. This is the coordinates x and y coordinates. At the point x is a by 4, y is a by 4. Okay, next we move on to the solution part. Root x plus root y is equal to root a. Differentiate with respect to x, we get 1 by 2 root x plus 1 by 2 root y dy by dx is equal to root a 0. Then dy by dx is minus root y by root x. at the point. Coordinates is given. Put x is equal to a by 4 and y is equal to a by 4. We get y1 is minus 1. Differentiating 1 equation 1. This is equation 1 with respect to x we get. So it is a second order differentiation. Apply the quotient rule. Numerator and denominator both are present. Apply the quotient rule and differentiate and simplify. We get finally root a by 2x root x. Okay, again simply at the point a by 4 we get d square y by dx square is 4 by a. Next we have to take the radius of curvature. Rho is equal to 1 plus y1 square to the power of 3 by 2 divided by y2. Substitute 1 plus y1 square. What is y1 here? Minus 1 to the power of 3 by 2 divided by 4 by a. Here 1 plus 1 2 to the power of 3 by 2 4. Finally on simplifying this we get the radius of curvature a by root 2. So that is, next we move on to example 2. Find the radius of curvature at any point t on the curve x is equal to a cos cube t, y is equal to a sin cube t. In the solution part, x is equal to a cos cube t, differentiate with respect to t. X is a function of t, dx by dt is minus 3a cos square t, again function of function cos t is minus sin t. Y is equal to a sin cube t, dy by dt is 3a sin square t cos t. Then find out dy by dx. It's a parametric equation. Then we have to write dy by dt by dx by dt. So on simplifying this we get y1 is minus tan t. This call it as equation 1. Again differentiate equation 1 with respect to x. We get d square y by dx square is equal to, it's a function of t is there, for that tan t derivative is minus secant square t into dt by dx, which is equal to minus secant square t into dt by dx. Here dt by dx is minus 3a cos square t sin square t. On simplifying these two terms we get y2 is 1 divided by 3a cos to the power of 4t sin t. Then radius of curvature rho is equal to 1 plus y1 square to the power of 3 by 2 by y2. Simplifying on y1 and y2, substituting y1 and y2 and simplification, we get the required radius of curvature. Rho is equal to 3a sin t cos t. Thank you.